Hello class, because we were not able to make it today and have our actual lecture, what I wanted to do is I wanted to make a video about X-ray production so that we are not behind. So this is going to be chapter 7 in our book, and a lot of it should be reviewed. X-ray imaging systems, the primary function, as we've already talked about, is to accelerate the electrons from the cathode end to the anode. And remember, it's very important that we understand that it is going in one direction, and because of that one direction, we are able to create X-rays. So it's cathode to the anode, and if we were to reverse that, go from the anode to the cathode, that would not make sense. And the reason, again, it does not make sense is because we are working at the cathode, we are heating up the filament, having thermionic emission with the electrons. Then after that, we are creating our source, which is the electrons. We're giving it the kVV push to the anode, and the stopping at the anode is what eventually is going to create that X-ray. So the three primary parts is the operating console. It has to be low voltage because, again, that is the area that we are going to be controlling. And again, low voltage just means that we don't get shocked. The high voltage generator, the X-ray tube itself, again, the whole system, when we consider the line coming in, 210, 220, everything that we deal with before the tube itself is going to be AC. And then for the tube itself, we need DC. And that's when we introduce our rectifiers and our diodes. So the X-ray tube is designed to provide a large number of electrons with that kinetic energy. And again, the kinetic energy is going to be our kVp and move it towards the small spot in the anode. And there are several obviously different names that we have for that. Focal spot is one of them. The systems themselves, all electrons have the same mass, so therefore electron kinetic energy is increased by increasing the kVp. Remember, all electrons are made equal, so it's a kVp that is going to make the final resolution of what we want to achieve. And as the electrokinetic energy is increased, both the intensity, quantity, and the energy quality of X-ray beam is also increased. Again, you have to choose those terms interchangeably. How intense it is quantity, which is a number. The energy itself is quality, and that's kVp. So again, intensity, quantity, mass are all the same category. Energy, quality, kVp is all the same category too. Also kVp, we have another word, and we could use the word penetrability. Electrons traveling from the cathode to the anode are going to be making the portion of the X-ray tube current that we are going to be calling the projectile electrons. So again, cathode to anode, we have, instead of just calling them electrons, we're going to call them projectile electrons because they're moving. And then approximately 99% of the kinetic energies of those electrons is converted to heat. The other 1% is used for the production of X-rays, and from that 1% to, as far as what actually constitutes a image, it's almost saying like the 1% of the 1%, which is pretty much nothing when we look at what eventually is going to hit the detector, our image receptor, and actually make an image. But within the tube itself, our loss in kinetic energy has to do to heat. Everything else, when it escapes the X-ray tube and it's going around, it's pretty much its interaction with the atmosphere and the patient. So the first interaction that we're going to be talking about is characteristic radiation. So that is produced when the projectile electron, again going from the cathode, ionizes or removes. Again, ionization is removal of the electron of an inner shell electron at the target atom. Again, the target is the anode. As the inner shell void is filled by higher energy outer shell, a characteristic X-ray is emitted, and that is the cascade from going to the outside coming in. The difference in the energies between the binding of the vacant shell and the outer shell is the characteristic energy. The effective energy of the characteristic X-rays increases with the increasing atomic number of the target element itself. More on characteristic radiation. So when the electron, that is the projectile one, so the ones that are coming from the the cathode, ionizes something at the target, it removes the K-shell. Again, and you have the temporary void in the K-shell. This is a highly unnatural state for the target, because what you want to do again is you want to be stable, so the outer shell electron falls into that void of the inner. Because of the electron binding energy for every element is different, the energy of the characteristic is produced at different rates. The effective energy of characteristic X-rays increases with increasing of the atomic number element. That is always true. So when you have both things that are increasing, that is a positive correlation. So here's our image coming in, starting with the top left ionized K shell, and then going to the right projectile electron, and then you look at the characteristic X-rays. You see that there is something coming in. You see the arrows kicking out that K-shell electron. So when you are kicking out that K-shell electron, you ionized the K-shell electron. As a result, what you have is you have after that, in the blue dotted line, the projectile electron, and then from there on you have the characteristic X-rays that are actually produced and that loss of energy. Characteristic is done. Now we go into the other guy, bremsstrahlung radiation or Brems radiation. Before we continue to this, just understand that with characteristic, it's the inside K shell that has to be removed, ionized, for that to happen. With Brems, they're produced when the projectile electron, again, projectile electron is the one that's coming from the cathode, going to the anode, it's slowed down by the nuclear field of the target atom nucleus. So there's slowing down. As the projectile electron passes by the nucleus, and understanding that the charge of electrons is negative, the charge of the nucleus is a positive. So understanding magnets and understanding the charges, you have to understand that a negative and a positive are going to attract. So by this electron, the projectile electron, coming closer to the nucleus, because the nucleus has in a sense, a bigger pull, because it weighs a lot more in the nucleus than the atom electron itself, is going to pull it, it's going to lose energy, and it slows it down. So it changes its course, and it goes in a different direction, and it reduces the kinetic energy. Again, the kinetic energy is the energy of motion. This loss of kinetic energy reappears as the X-ray Brems photon. So again, it is the loss of the energy that is going to appear as the Brems photon itself. Most X-rays are Brems in the diagnostic range, 20 kVp to 150 kVp. And again, the next part is very important to understand the difference between the two. Characteristic X-rays require an X-ray tube potential of at least 69 kVp, or no useful characteristic X-rays are produced. So therefore, the X-ray beam is all Brems. So again, just to summarize it, we have characteristic. It has to knock out a K-shell. K-shell, when we look at the number of 69 kVp, that comes into play because the binding energy of the K-shell electron is 69 kVp. So what you need to have is you need to have something that's going to be equal to that energy to kick it out. And again, by kicking it out, we are talking about ionizing it. So anything less than 69 kVp, characteristic X-rays cannot occur. It's at least 69 or more. As long as you got that down going into Brems, Brems occurs in all energies, because all it's doing is the closer you are to the nucleus when the electron is going, the closer you are, the more energy you're going to lose. because of the force of the nucleus, the further away you are from the nucleus, the less energy you're losing. So, because we could never really be for sure to see where that projectile electron is going to be towards the nucleus, that's why the energies have a huge variation. And because of BREMS, a lot of times when we talk about KVP itself, kilovoltage peak, we say peak because peak is going to be the highest number. So if we, for example, said 120 kVp, 120 kVp as far as the push, that is going to be the highest. Theoretically, we're going to get values that are going to be lower. And the values are going to be lower because the interaction is not for certain of how it's going to occur. So bremsstrahlung, in a sense, is the same thing as that, because when we have those interactions, we do not know the kind of energy that is going to be lost. And again, the kind of energy that's going to be lost is the X-ray photon that we're going to have. So that's why they're kind of all over the place. So again, BREMS is all energies that could occur characteristic. You need at least 69 kVp because you're concerned about the K shell that's in the center by the nucleus. As low energy BREMS X-rays, a low energy BREMS X-ray results when the projectile electron itself is influenced by the nucleus. Then the maximum energy of X-rays occurs when the projectile electron loses all of its kinetic energy and again simply drifts away from the nucleus. So the nucleus is so strong that if all the energy is lost, that is the most you're going to get. BREMS X-rays occurs with energies between the two extremes, and obviously will occur more frequently. So there is your BREMS. When you are looking at the different colors, so there is a darker blue and the lighter. You look at the lighter and you look at the darker. It's pretty much showing you that the closer that it is to the nucleus, the bigger curve it's going to have, so the bigger loss of energy and so on. So for example, the one that's a darker blue, obviously it's pretty sharp turn, so that means it's closer to the nucleus, and you look at the nucleus charge, it's a bunch of pluses, the electrons are always negative. So because of the attraction of the nucleus, what you get is to the bottom right, high energy bremsstrahlung X-rays. You look at the other guy, the lighter blue, again, the force of the nucleus still pulls it, and then you look to the left, you get low energy bremsstrahlung radiation. When you look at the X-ray emission spectrum itself, again, if you could stand in the middle of the useful X-ray beam, catch each individual X-rays, and measure the energy, that is what we call the X-ray emission spectrum. There's a figure in the book in 710 that actually shows it. So data on X-ray emission spectra are needed if one is to gain an understanding of how the influence and changes in KVP mass and atom filtration actually affect the quality of an image. We'll go over those in a second. So there it is. Very, very important when we are looking at this. Let's look at it. The x-axis in the bottom is X-ray energy, keV, electron volts. To the left in the y-axis we have the number of X-rays. So first thing we're going to do is we are going to look at the blue, which is BREMS. Very important to look at BREMS because what we're going to see is that look at 0 and it goes up to closer to 100. So it peaks at a certain area, but the nice thing about it is that it occurs in the whole x-axis. When we look at the characteristic X-rays, notice that the line is purple. The line purple begins at 69. Remember, that is the binding energy of the K shell. So I have to at least meet the binding energy of the K shell for me to start having characteristic X-rays. So the discrete energy of characteristic X-rays are characterized in the difference between the electron binding energy and a particular element. Again, the one that we are more concerned about is the K shell, which is the closest one to the nucleus. Characteristic X-rays have precisely fixed energies, and again, fixed energies, versus bremsstrahlung, which is all over the place. The relative intensity of the K shell X-rays is greater than that of the lower energy characteristic X-rays because of the nature of the interaction. So now when we look at Brem's X-ray spectrum, when an X-ray tube is operated at 90 kVp, again, 90 kVp, Brem's X-rays with energies up to 9 kVp are emitted. Again, notice that it says up to 90. So obviously that means we can get less. The greatest number of X-rays is emitted with energies approximately 1/3 of the maximum. And that could just vary based on the machine. The number of X-rays emitted decreases rapidly at very low energies. So the different factors that are going to affect the X-ray spectrum itself. So the first thing is integration. It's the total number of X-rays emitted from an X-ray tube. So you add together the number of X-rays emitted at each energy over the entire spectrum. The farther to the right, when we look at that spectrum, the chart, the higher the effective energy or quality of the X-ray beam. So again, energy quality. When we are considering quality, we're considering, again, kVp. The larger the area under the curve, the higher the X-ray intensity or quantity, which is a number. So again, when we are moving to the right, as we notice the x-axis here is X-ray energy. When we look at the y-axis, that is increasing. We're increasing the number of X-rays or the quantity. So again, that is the X-ray emission spectrum. So when we look at MA and mass, if one changes the current from 200 to 400 mass, so again, we're doubling it, while everything else is constant. Twice as many electrons will flow from the cathode to the anode, and the mass will double, because again, you went from 200 to 400. A change in MA or mass results in a proportional change in the amplitude of the X-ray emission spectrum. Again, when we are considering the amplitude, that is going to go between the 0 and up, and that is what amplitude itself is defined as. Each point on the curve labeled 400 MA or 400 mass is precisely 2 times higher than the associated label of 200 MA or 200 mass. Thus, the area under the X-ray emission spectrum varies in proportion to the changes in MA or mass, as does X-ray quantity. So again, the word X-ray quantity, mass, MA, is going to be responsible for that area when we look at it. The amplitude, which is the area that's going to be under the curve, all means the same thing. When we're going to the right, that is when we're concerned about kVp. And here's kVp. As the kVp's increase, the area under the curve increases to an area approximately the square factor of which the kVp was increased. Cover that in a second. All it's talking about is a slide, and a few slides later we'll explain that in a second. X-ray quantity, again, quantity is a number, so we're talking about mass, increases with the square of this factor. Cover that in a second too. These figures can be explained by the 15% rule. So with the 15% rule states that a 15% increase in kVp is equivalent to doubling the mass. So at low kVp, such as 50 to 60, approximately a 7% kVp increase is equivalent to doubling the mass. And you're thinking to yourself, okay, when am I going to do this, or why do I need it? Before we answer that question, it is important to understand that the 15% rule has to do with an increase or decrease in kVp. We do not do that increase or decrease with mass. So by understanding that, so we're saying a 15% change in kVp is able to double the mass or reduce it by half. So just by understanding those numbers, kVp is going to have a bigger factor at controlling what we do. And that is why we only have to increase it or decrease it by 15%. So again, when we are considering kVp and mass, let's say we are using the 50 to 60 kVp. Let's say we are doing something like, just make it very easy, 100 kVp at 100 mass. Okay. we get an image, we have to increase the density. We'd like to increase, when I say density, we're trying to increase the mass. So there's two things we could do. We could actually increase mass itself, or we could increase kVp and use the 15% rule. If I were to use the 15% rule, let's do it a different way. If I were to change the kVp from 100 to 115, so I went up on kVp, what do you think that is going to do to my mass? So when I'm going up with my kVp, that is going to be almost the same exact thing as doubling my mass. So just by increasing kVp by 50% has capability of doubling, in theory, doubling mass. So we'll cover that in a few different lectures. A tube potential above 100 kVp, a 15% kVp change may be necessary. That's what I'm using for my example. So again, with 100 kVp, we're only going to have to go up 15% to get that double. Or if we like to do it on the other end, if we are, like, for example, overexposed, and we'd like to change to the kVp instead of the mass, we could go to 85 kVp, which is going to be equivalent to halving the mass. In theory, increasing the kVp by 50% doesn't double the intensity, but is equivalent to doubling the intensity to the receptor. So again, when we increase the 15% in kVp, we are not doubling the intensity, it's equivalent to it. So as far as filtration is, adding filtration to the useful beam reduces X-ray beam intensity while increasing the average energy. Very important, and I'll say it now. Generally, there's different things we could use for filtration, but in the tube, we generally use aluminum. And again, a lot of stuff that we're going to cover is usually going to be between aluminum and lead. It's so important for you to understand that you cannot use lead. So we're in the X-ray tube right now. What we're trying to do is get rid of low energy X-rays, because low energy X-rays are going to be responsible for what is called a skin dose. So they're useless. All they are going to do is just going to be bad for the patient, give no good detail, and again, that's why we call them skin dose. So by using filtration, what filtration in a sense does, it just puts a little filter that is not going to completely stop the beam. It's just going to get rid of the low energy X-rays. By getting rid of the low energy X-rays, what you do is you increase the average energy. So just give you some numbers. If I give you a few different numbers, if I say 100, 90, 90, 90, 80, 70, 60, and the next three numbers, the next number after 60, let's say it's 10, 5, and 7. So if we were to take those averages, the 10, 5, and 7, if we were to put those within the average, what's going to happen is the average energy is going to be low, because you have three low numbers that you're averaging with everything else that's a high number. So if I were to take those three low numbers and do another average, again, that's when you have the increase. So that's pretty much all filtration is doing, is getting rid of the low energy X-rays just so that the average energy, which is going to be useful, actually makes that image. And again, it's just not skin dose. So skin dose doesn't do anything for us or the patient. Adding mold filtration effectively absorbs the low energy X-rays than the high energy X-rays. Adding filtration is also called hardening the beam. So that's just another way of somebody saying hardening the beam. And when you think of something hard, you want to get rid of something soft. And in this example, of something soft is going to be the low energy X-rays. The effect on target material. So increasing target, again, when we say the word target, when we think about cathode to anode is where we are producing, we're adding current to the filament, we're heating up thermionic emission, and then after that we apply our kVp and push it through to the anode. So when we say target, we are talking about anode. The atomic number enhances the efficiency of X-ray production and the energy of the characteristic and Brem's radiation. So the atomic number is a big deal. The higher the atomic number, the more chances that you're going to have the characteristic and the Brem's. Tungsten is the primary component of the X-ray tube targets, but some specialty X-ray tubes use gold as the target material. Again, the most important thing that you have to understand about tungsten is, one, we use it because it's cheap. Two, we use it because it has a high melting point. And previously, we talked about 99% of what we're doing gets converted into heat, which is a loss energy. So by having tungsten, obviously you could withstand high amounts of heat, and that's why our X-ray tubes, even though obviously they still fail, they last a lot longer. Elements of low atomic number also produce low energy X-rays. And that is it. If you guys have any questions, you can either email me, put it in the comments here, and we will be going over everything again next week. And please understand that all this lecture is going to be fair game for the final, and also a possible quiz for next week if that were to happen. Have a great day, and see you guys next week.